Thank you so much for that kind introduction, and thank you everyone for being here. I'm so glad for the opportunity that I have today to share the research I've done in the past few years. So I would like to start by sharing this picture of my hometown, Isfahan in Iran. This is a city that is very famous for its river and its historical bridges, and a few years back it suddenly dried, and what we all first thought it was because of less rainfall in those years. Later we find out it was actually bad management and planning. And as I was studying the hydrology of this region for my master's, what was so interesting for me was that I realized that way before that the river dried up, there was actually studies that was telling us that the development plans of the region will lead to the river drying up. And I always thought with myself, if we were using that information in time, this would never happen to our city. And so that really prompted me to become interested in to see how we can use science to better inform our decisions in a timely manner. And that's what I did in my dissertation. I looked at 3 different environmental issues that each would represent a unique kind of challenge about how we can incorporate earth science in policy. Subsea, permafrost, fire regimes, and water megaprojects. And so normally what we do when we want to inform decision, we have an understanding of the system and we try to communicate that with the public and policymakers, and so based on that information they can make management decision. However, there are many obstacles when it comes to this communication. Mostly the uncertainty of science and complexity, it prevents from a very efficient kind of communication. And so approaches like expert assessment, which I use in my dissertation, these are approaches that will lead to a more efficient communication by supplementing models and empirical methods to communicate our best available knowledge for public and policymakers. And this is by basically, for example, we would include, for example, we know about some feedbacks in the Earth system, but we don't know enough to formally include them as a quantitative values in our models, but we do know they exist. So expert assessment approaches kind of let that kind of informal knowledge to be added to those formal knowledge, and we give a better picture to policymakers. And so what we were mostly interested was we wanted to see how these different Earth systems will respond to climate change in the future. And for that we used 3 RCP scenarios, from a very least warming RCP 2.6, a medium version scenario RCP 4.5, and a high emission scenario RCP 8.5. And what we did was, for each of these case studies, we will go through the literature of the scientific documents, the policy reports, and identify the gaps to see what is needed for policymakers and what is missing there. And so this was the format of most of the questions of the surveys that we designed. At the first part, we would ask experts to provide us with 3 values, 3 quantiles of 5% central and 95%. So basically, each expert will provide a 90% confidence interval that they will think that the true value of that question will be somewhere between, there's a 90% chance that the true value will be somewhere between these values. And then we also ask them for telling us what is their confidence and expertise level regarding that specific question, how did they generate that question, and what are the largest sources of uncertainty that are currently regarding to that specific question. So with that, I will move on to my first case study, his first chapter, with the title of Subsea Permafrost Carbon Stocks and Climate Change Sensitivity Estimated by Expert Assessment. So every day more evidence is found that we are reaching tipping points in the Earth system that will negatively affect us. And one of these really important feedbacks are permafrost carbon and methane hybrids. And the reason that these are so important is that even though permafrost only contains about 12% of the Earth's surface, it is the largest carbon pool that we have on our Earth. And only in the soil profile alone, there's twice as much as carbon that is in the atmosphere. And since the 20th century, a lot of attention has been raised about the permafrost, the potential permafrost carbon feedback, where scientists were concerned that with global warming, the carbon that was trapped in this zone for thousands of years will thaw and get into the atmosphere. Yet not until recently it has been formally acknowledged in policy reports, mainly because of very limited data. So for example, these graphs are showing the permafrost projections in the IPCC report. For example, here is showing how different aspects of it will change for different RCP scenarios, and these are also different projections for the cumulative carbon change. And as you can see, different studies can have very different projections based on the models they use. And one of the reasons that we are so uncertain about these amounts is that because there are so many things that can contribute to the carbon balance of the permafrost region. For example, what is the rate of thawing in different regions? How will this thawing change the characteristics of the soil and microbial communities? How will different disturbances like wildfires or water availability during the growing season will affect the carbon uptake? So all of these uncertainties are reflecting in the models that we depend on. And the subsea permafrost specifically, I think, is the most mysterious part of the permafrost region, and it's still only acknowledged as an unknown, just this big mystery. And we sometimes, however, hear about it in the media a lot. We have like mixed messages about how abroad this feedback is going to be. You maybe heard about the methane bomb a lot, that there might be a chance that we will have a lot of greenhouse gas emissions suddenly from the Arctic Ocean. And this is mainly because studying this system is extremely difficult, and right now our data is very limited and patchy. And so just a little background, more background about subsea permafrost. So here you see at the last glacial maximum about 26,000 years ago, we had the continental shelf permafrost, which had a lot of organic matter in it because of undecomposed plant and animal material during the years. And as the global sea level rise, this part of the continental shelf submerged, and so consequently the thermal regime and of it changed, and ever since the subsea permafrost is degrading. And as it's degrading now, the microbes are using those carbon stocks as food, and they're generating different greenhouse gases. Now the problem is that we don't know neither how much carbon is in the subsea permafrost, neither how much sensitive they are to climate change, and how much it will be released from this area. And so the questionnaire that we designed had about 15 questions that they could be summarized in this. We wanted to know mainly, well, how much carbon we think is in the subsea permafrost, how much of this carbon is going to be thawed, and how much it will get into the atmosphere. And so we designed a questionnaire based on that, and designed and distributed that to about 120 permafrost researchers, which is just the distribution of them, when we got responses from about 25 experts. And so we asked about the current and past carbon estimates, which I will pass those because of time. But later, what we wanted to know about the future is that, as I said, many different factors can affect the carbon balance in the permafrost, and we wanted to know what percentage of the current carbon stocks can potentially be affected regardless of climate change scenario. So here, for example, we have the yellow panel is showing the percentage of the potential affected of soil organic matter, and the purple panel is showing the methane stocks, about what percentage of these can potentially be affected. And as you can see, and before that, so each dot is showing an expert, and the lines are showing the range that they provided, and the black lines are also showing the median of each of the quantiles. And so as you can see, especially for the year 2050 and 2100, a pretty small percentage was predicted to be even affected, and like 3% and 8% for both these the organic matters and the methane stocks. And and if you see at the ranges, you see that methane is even maybe less sensitive to change than organic matter, which can potentially, because of the location of these hydrates that are very deep, and so they have a pretty stable zone. And so at the present time, what was estimated is that 18 megaton carbon is getting out to the atmosphere in the form of methane. About 25% of that will get into the atmosphere. 38 megaton carbon of carbon dioxide in the form of carbon dioxide, which also just want to remind that these are just only the central estimates, and the actual values they provided was very wide, that you can see in our paper. And so this is what they estimated for the current time fluxes of greenhouse gases, which is kind of equal to a small European country at the time. And so we wanted to see, okay, so how do you think these fluxes are going to change in the future because of under different RCP scenarios? And so as you can see here, each color is representing one RCP scenario, and these are the fluxes for carbon dioxide and methane. And as you can see here, the first thing that we noticed, that all of the predictions of all experts, that similar to the previous one, the dots are each dot is one expert, they all thought that the subsea permafrost is going to have a positive carbon only release, a positive carbon balance, meaning that it will only release greenhouse gas. And this is unlike the terrestrial permafrost, which both uptake and release is predicted for this area. And also, as you can see, for the two milder RCP scenarios, RCP 2.6 and 4.5, these the prediction was that a very small amount will be increased to the current releases. Like as you can see here is 10%, and most of our spread until 2100 is under 10%. But the thing is that really important, as you can see, as we go with a more extreme climate change scenario, RCP 8.5, not only that this percentage can increase, but our uncertainty also increase, and we have wider ranges, especially for methane. And so when we convert all of these to carbon dioxide equivalent, and when we look at the cumulative values until 2300, which here you can see for each RCP scenario, and the pink one is showing carbon dioxide, the methane is showing, the green one is showing methane, we can see that the cumulative amount is pretty substantial. And also, but we should have in mind, these are only central values, but if we include the uncertainty range, we see that these values can be much bigger, and especially, again, with RCP 8.5, this uncertainty will increase significantly. And so overall, how does the subsea permafrost contribute to the Arctic carbon feedback? When we compare our results with results from studies for the terrestrial permafrost, we can see that for the terrestrial permafrost under RCP 4.5, an uptake of of greenhouse gases is predicted for the region, and the subsea permafrost can potentially offset that uptake by 27% by 2100 and 160% by 2300, meaning that by 2300 the subsea permafrost alone will release more greenhouse gases that the terrestrial permafrost is able to uptake. And for RCP 8.5, where only a net release is predicted for this region, the subsea permafrost is predicted to increase that by 32% in 2100 and 8% in 2300. And so overall, the key points of this study, I think, was that we should have in mind that unlike what the media wants to tell us, when we look at the history of this system and how it has changed during thousands of years, we can say that these carbon stocks are pretty stable, and the climate force from this is pretty slow. However, considering how small this place is, and it's about 5 times smaller than the terrestrial permafrost, it is definitely a hot zone, and it should be it will affect the overall Arctic carbon balance. all of our experts said that inadequate field data is the main reason that we are so uncertain about these estimates, but also the fact that we are ignoring in our studies the link between the terrestrial permafrost and the subsea permafrost is also a really big contributor, because, for example, how will the runoff of the sediments from the terrestrial permafrost on the subsea permafrost, how will that change conditions for the subsea permafrost? That is not really studied yet, and so we need more synthesis activities between different research groups so we can better understand these links. And human emissions, of course, can play a really important role in about how much the amount of greenhouse gas released from the subsea permafrost. About 75% of the greenhouse gas released from this region can be prevented if we go with a RCP 2.6, the milder scenario, compared to RCP 8.5. And just in the end, so for this chapter, is that how does all of this should care for policy? So United Nations have a target to limit warming by 2 degrees or 1.5, and for that we have to know how much carbon we have left to burn and at what rate should we burn these. And so as you can see here, this is the remaining carbon budget, and here is the unrepresented Earth system feedbacks, and which permafrost is one of these Earth system feedback that is not represented in most of these models. So first of all, there is a chance that we are overestimating about how much carbon is left for burning, but this uncertainty of these Earth system feedbacks have really been distracting and delaying action for human emissions. And regardless of all of the uncertainties that we have, there is a really good agreement between the permafrost scientists that even in the worst case scenario, and for RCP 8.5, by the end of the century, the greenhouse gas emission from this region is not even it's not even close to what human emissions are. And so that means that we should focus mostly on human emissions, and that should not really be distracting our policy actions. Okay, so with that, I will move to my next chapter, assessing changes in global fire regimes using expert assessment. So as you know, human activities like land use change and climate change, they have reshaped wildfires globally, and now a lot of fires in many regions are exceeding their historical patterns and causing many negative consequences that are concerning different countries. And in order for us to effectively manage and plan for these fires, we need to understand what the fire regime of a region is, and how different components like vegetation and climate, how their interactions will affect a fire regime in a place. And the problem is that, well, there's many different things that interact together to determine a fire regime of a place, and those interactions, we cannot currently capture this in our models, and there are so many things that we are now missing in our models that are important for fire regimes. And so here you see that we had two main concepts in our paper. So the first one is the concept of fire regime, that is that in our paper we define that based on the spatial components and the temporal components of the fire. So for example, what is the usual area, the burn area of a fire, what is the usual, for example, frequency and different characteristics. And also state change, which we define as a large and sustained departure from a system behavior. So for example, here you see at the Mediterranean, so this was our first, this is a fire regime, and then with different drivers, for example, like fire suppression or global change, like one of these characteristics or some of them can change. So for example, here the frequency and area has changed, and that is called what we call like a fire regime has entered like a new stage. And so in our paper, we wanted to address that uncertainty. And so what we asked, we designed a questionnaire that included many questions that are summarized here. So first we wanted to know how have fire regimes varied during the Holocene, the past 12,000 years? How likely are fire regime state changes under different future climate change scenarios, what components of the ecosystems will change because of these new fire regimes, and what type of human activities are best to mitigate these negative impacts. So we distributed our questionnaire to about 430 fire researchers, and we received 123 responses from 98 experts. And for each expert provide values for a biome inside of a continental region of their expertise. So at first, when we look at during the Holocene, we see that in different regions, fire regimes have changed a lot. And these are the times where our experts identified the 3 largest fire regime changes, which, as you can see, at the late Holocene, the last 4,000 years, most of our responses indicated changes for that period of time. And especially when you look at the blue and purple part, which is it represents since the industrial era, we can see that there have been about a 10-fold increase in the rate of fire regime changes globally. And looking at the drivers, well, climate has been was the major fire regime driver that was identified. About 50% of our responses indicated that. But however, as you get closer to current time, human influence became more dominant. And as you can see, of course, this is different in different regions. So, for example, in the West Palearctic, mostly Europe, humans have been a major driver of fire regime time for a very long time. But in some other places like Australia or America, it has been a little bit more recent. And when we ask about, well, how will these fires, how likely are these fire regimes are going to change in the future, as we expected, with higher emission scenarios and longer in time, there is a higher chance of changing fire regimes. Like here, most of them are about 80 to 100%, and these are lower for RCP 2.6. However, one thing that is interesting to consider is that unlike many other Earth systems, that it usually takes a long time for them to respond to changes. For fire regimes, even in the year of 2050, under higher emission scenarios, many of our biomes they were estimated to have a higher chance of 50% to see some sort of fire regime change. And for some biomes like tundra, even under RCP 2.6 in the close time, a 60% chance of a fire regime change was predicted. And when we and our experts estimated that all of these fire regimes will mostly lead into bigger fires, more frequent and more severe, and with the only and that will increase again with the RCP scenario and years. And the only exceptions here are the biomes that are fuel limited under warmer scenarios, such as deserts or temperate grasslands in Africa. And again, when we ask about, well, how will these affect different components of the ecosystem for all biodiversity, carbon stocks, and ecosystem services, there was mostly a negative effect was predicted, except from some places. But for albedo, a slightly increase was predicted for at least the year 2100. That shows that there might be a stabilizing climate feedback for a short while because of the new fire regimes. And at the last section, we asked them to provide us some suggested interventions about like what we can do to minimize these effects and what kind of human interventions can be effective, which here I summarize in different categories, and these are in order of the spatial scale of the intervention. Overall, most experts believe that some sort of human intervention will be very useful. And there is different level of agreements, of course, regarding different interventions. For example, prescribed burning practices, indigenous burning, that was generally perceived as a very positive action, but other actions like fire suppression, there were kind of mixed opinions depending on the region and the expert. And most of our experts believe that under RCP 8.5, the warmer scenarios, we will have a less capability of controlling these fires, and those human interventions will be less effective. But about 70% of them believe that under RCP 2.6, we actually will have a good capability of controlling and mitigating the negative risk of the new fire regimes. And so overall, the key points of this study, I believe, was that, first of all, there is a really good agreement between experts that under higher emission scenarios, we will have a risk of more higher fire activity in most regions. And this is really important for climate mitigation policies, especially those that involve decarbonization using forestry. And because we need to evaluate to see, as we are planning for forestry to remove carbon, how will this risk of new fire regimes offset that? And the past fire regimes, the history of fires, and how the climate and vegetation and human actions, how they interacted together, that is very that is something that can give us a lot of good information about, for example, what will be a good vegetation for a certain area, and that will minimize the risk of the new fire regimes. And yeah, so, and with that, I will go to chapter 3, water megaprojects, past decisions, and future implications for policy. And this chapter, unlike the two other chapters that we were mostly concerned about, we were addressing the complexity of science and uncertainties. In this chapter, we were mostly looking at other factors that was preventing the use of science for making decisions. And for this, so in megaprojects in general, they can be defined based on different characteristics, like, for example, their budget, their complexity of infrastructure. But from an ecological point of view, we can define water megaprojects as any kind of infrastructure that will significantly change the form of the landscape and the water regime. And we humans have been manipulating watersheds for thousands of years for like agriculture uses, but since the Industrial Revolution, our capability, of course, of building mega infrastructures increased, and during that time, we have built about 45,000 large dams. And there have been so many studies that is telling us that about the negative social and environmental impacts of these projects. But not only that, there have been many studies that show us that even these projects are not even really good at their main purpose, that is, for example, increasing the water supply in long term. And despite all of these studies and these negative evidences that we are still considering these water megaprojects as a strong solution for increasing our water supply or energy. So for example, in this study, you can see that the different megaprojects that are planned globally for the year 2050, which is mainly for agriculture uses. And so we wanted to look at, we look at the decision-making process, and we wanted to see that what factors are actually making decision makers so interested and motivate them to use mega infrastructures for solving their water problems. And we chose a set of water examples globally to see, look at their history and their decision-making process to identify some main factors. The first example is from the Colorado Basin, which is very, it's a very important case study because it is the pioneer in modern water engineering. And for example, the Hoover Dam has been told that has inspired many governments to build large dams. The Amazon is one of the most heaviest dammed basin in the world, with about 81 dams, and about like hundreds and more dams are planned to be built there. And it has a very unique environment, and unlike other places, it is actually very water abundant. So it does have different challenges over there. The Markerwaden project it's a restoration project in the Netherlands, and it's an interesting case because it's in a country, Netherlands is very famous for its good water management actions, and so we wanted to see in that context what kind of problems can happen. The Urmia Lake in Iran once was the second largest salt lake in the world, and in many other many other salt lakes in the world, it has been eventually dried because of heavy agriculture practices. Since the revolution of Iran in 1970, about 52 dams has been built in this basin, which has taken about 85% of the water resources of the lake, that which led it to dry. The Lesotho water transfer project is the largest binational water transfer project that moves water from Lesotho, which is water abundant, to South Africa, which is water poor, and it also provides hydropower energy for Lesotho. The South-North water transfer project in China is the largest water transfer project in the whole world, and it is important because of its political purposes. The Three Gorges dams is the largest hydropower dam in the world, and it has been a lot of controversies about building this because of both the cost and the very severe social impacts that it has. It did submerge about 13 cities, and 100 villages were submerged for building this dam. And the Ord River water scheme is a water scheme developed in northern Australia, which was with the purpose of expanding agriculture activities in that region. And so the first thing that we saw in all of these case studies is that there is a main problem with defining objectives of stakeholders when it comes to water decisions. And because the nature of water, it does, like every decision we made in the water sector, it will affect multiple scales from local to global, and also it will have effects in both short term and long term. It is really hard for us to define clear objectives, and that is really missing in many of these decisions. And so, for example, and so these water mega projects are usually, these are tools as an intermediate objectives to get to more fundamental objectives of the society. And because we are mostly focused on short-term water supply for different reasons, like political stability, for example, in Iran and China, that's a very big concern. So we think in that context, these are more justified rather than in countries that they're mostly focused on sustainable development. And so water mega projects can be in conflict with other intermediate objectives that will prevent from sustainable development. Another really important factor is the factor of interest groups, and we defined here. So in general, in policy and management, these are groups that will affect the decision-making process for their own benefit. And here in our study, we mostly are talking about this well-organized, well-resourced interest groups, that they have a lot of power in governing water projects. And in many of our case studies, we saw that, for example, private construction firms, they push for bigger projects or unnecessary projects in that basin. And for example, Brazil is it's a really good example for this, where the private firms have a lot of influence on the government. And the government is yes, it is pro-dam building, and they create a lot of great conditions for these private companies. And these private companies have been taking a lot of advantage, and not only private companies in Brazil, but also other international companies. So for example, China is specifically very influential, has been very influential in dam building in Brazil, and one Chinese company itself has control over 50% of the international market of hydropower dam building. And not only that, but the hydraulic bureaucracies in some countries are also designed in favor of mega projects. So especially in Southeast Asia, these governmental systems are in a format that individuals working in these agencies will benefit if there have been more funding for their agency. And so they're also in favor of their agencies moving on with bigger projects. Another really important factor is the conflict of what scientists saying with values, and this happened a lot in our examples. So for example, in Colorado Basin, at the time in 1920s, the fast development of the western states was very important, and there's the Depression and the peace between, for example, the 7 states. So a lot of these prevented the decision makers at the time to listen to the proper science, which at the time hydrologists were telling the decision makers that the numbers at the in the water compact is based on an 18 years of a wet period, and the longer time data is showing that these are an overestimation of the available water in the river. Or for example, in Australia, the problem was that northern Australia was very depopulated, and for national security reasons, the government was very focused to expand agriculture activities and be sure that that place is populated enough. And so they ignored all of the economy analysis that was done for the scheme, and they went with the scheme, and it was not very, and from an economic point of view, it was a failure. The same thing, for example, with China, Iran, some of the other countries, they have a great value in national pride of having like the biggest infrastructure. So for example, in the Three Gorges dams, there was a lot of proposals that we can like, instead of building this very huge dam, we can do like multiple smaller dams, will be less risky, and there will be less consequences. But there have been told that the title of the largest dam, for example, was a very important value for the government, the same at Brazil and other countries. Mental models and decision alternatives, these are referring to when our beliefs and our understanding of a system, and so decision makers, like everyone, they have a certain beliefs about how a system works, and based on that beliefs, they will come with solutions. And the problem is that the biases our minds have. So once we come with a solution, our mind is kind of biased to adjust with new information, and we really just stick to that. And so in many of our case studies, we saw that a political leader at some time, they will come with this idea about like transferring water or building a big dam, and that, even if at the time that was not feasible to done, but that was like the main solution always on the table. And so all of like the research, everything that was done was evolving around that specific solution to see how will that be implemented. And there have been studies that show that in many cases of dam building, alternatives have not been considered. And so, and like as I said, so like when you add this with interest groups, yes, they will see this as an opportunity to like propose different kind of solutions based on what the one of those leaders said. But also there is some kind of like, one of the reason is like mostly in this project, engineers are the ones that are consulted. So for example, in the case of South-North water transfer of China, the private sectors had very limited influence because the government very much strict that. And so even though that was really strict, and but they still thought, oh, this will be the best solution to provide water for the northern states, which is politically very important for China. But there have been studies that show that, for example, 50% of the northern water has been decreased because of water pollution. And all of those factors will eventually lead to very biased risk and uncertainty and analysis that in general with mega projects, we see that the cost and benefit analysis have usually been very unsuccessful. And for dams, specifically for large dams, 100% overrun is the average global cost overrun for dam building. And like, for example, in our examples, the Three Gorges dams, for example, that was costed 5 times more than what was initially estimated. And as you can see, for some countries, this can go up to 500%. And one of the reasons here is like, well, first, these analyses are done by the promoters of the projects, so those interest groups, and then these the way the analyses are done, they're very heavily based on assumptions. So basically, it's really kind of easy to like change that assumptions and get the result that you like. And so, for example, at the South-North Water Transfer Project, both the World Bank and the World Wildlife Foundation, they have both done feasible studies for this, and one rejected the study and the other one justified it, just simply because they use different assumptions in their study. And so overall, the takeaway from here is that the first thing that we really need to do is that be better with defining our objectives when it comes to water problems. Like for example, in the case of the marker water project, even in that system, that is a pretty good water governance system, and it is a really recent project. Now that they want to evaluate the project, they have seen that the objectives that were defined were very short term, and it didn't include like the larger effects that the project can have. And so the company that was building the islands were not really accountable no longer for that larger and long-term effects. And so frameworks like the food, energy, water nexus, these can be very helpful for us to see water in a better scale, and that will also help us with a better stakeholder analysis that is very much lacking in our water decision, because it has to be on several scales and also include long-term stakeholders. Using diverse expertise is really important, and especially local knowledge. And as I said, most of these mega projects, when you look at, mostly engineers are the ones that are consulting these projects. And for example, when you look at Lake Urmia in Iran and Great Salt Lake in Utah, you can see how different this can be. So for example, in Iran, the government is still very much tending to rely on engineers for solving the lake problem. And so water transfer has always been their main solution. But in Great Salt Lake, the government is using a more diverse experts, and so you see also more diverse solutions and less risky solutions. Improving water education is really important, because there is a global problem that our education is in educating people about water cycle. It does lack the effect of human impacts on the water regime, and by improving that, we could hopefully fix this mentality that our default solution should be like for example increasing water supply rather than controlling our demand. And risk analysis are well, first of all, they we think should be done by neutral parties rather than the people who are benefiting from that project, and also they need to be more based on empirical data rather than strongly just depending on different assumptions. And also considering with climate change and all of the changes that is happening in our future, we really need to be having more resilient planning that can be flexible for different conditions, instead of just relying on single objective mega projects. And so overall, my overall conclusion for my dissertation is that we're living in a time that technology is fasting very fast, and every day our capability of increasing the of changing the environment is increasing. And so with that, we really do need timely insight to be sure we are making the best decisions and using that technologies wisely. In all of our studies, we saw that models are very they have their own limitation, and it's very crucial that we use diverse approaches, so we be sure that all sort of knowledge is included in our decision making. And another really important factor is, the last one, is the connection between different research disciplines. So right now, if you look at the most policy reports, they will define 1.5 as the ideal scenario. However, we know that with even under the 1.5 scenario, as we saw in both of our case studies, there are many risks with that scenario. And then on the other hand, the earth scientists believe that the 1.5 is the most realistic or very optimistic kind of scenario and greenhouse gas emission from an energy perspective, which that is also not true. With the developments in renewable energies, we have the capability of going much lower than 1.5. But then this connection between the different research disciplines has led that this kind of misconceptions have developed. And yeah, so and that I would like to thank my committee members for always guiding me and their always support. The BRI graduate studies for funding my research, the International Permafrost Carbon Network, the International Paleofire Network, and all of the experts that participated in her study and provide their knowledge and expertise with us, and my lab mates that were always their constant support and encouragement, and also my family that I think are there. Thank you.
So we'll have a closed session after this for the committee members. But anyone have a question they'd like to ask Sarah?
So I'll ask one, Sarah. I don't know if this is a question you can even answer because it's so broad, but on all of your chapters, and it seems like everything we hear about the climate, there's this disconnect between what the general population knows and understands and what science is telling us and what policymakers. I mean, how have you seen anything that says this is a way we can bring them together? I mean, it feels like everyone's just butting heads, and
Yeah.
I mean, like I said, so this is kind of out of the scope of your presentation, but it seems to be like that's the key, is trying to figure out how to bring everyone to the same table or conclusion.
Yeah, well, so one of the things that we see is that, for example, a lot of researchers, they are reluctant to participate in this kind of studies, and they're really they want to have I feel like not all researchers understand how difficult it is for people to connect the data together and see the bigger picture. So I think the most responsibility is on the researchers to connect those dots and provide the better picture for the public. And yeah, so I think there should maybe be a more systematic way where universities even or research groups, they have a better system that experts can provide their opinions more efficiently. So for example, when it published, when we want to from the time that you have your study and you find your data and the time that it's published and it's available to public, there can be several years of a gap. So I think it's really important that we have a more efficient system in communicating that science. And also on the policymaker side, I feel like the problem is that they rely too much on maybe single expert advice, and from their side, I feel it also they need to have a more they should listen to more diverse groups, especially in a lot of our things we see indigenous knowledge has been such an important knowledge that is missing from all of these decisions. And yeah, so I think that's I think it's mostly those two groups can maybe do that things.
I have, I don't know what it is. Maybe well, a couple of things. So, why did you choose permafrost, fires, and the mega water projects? And do you think there's any other climate-related phenomena that we can add to your study? Because I think with Shannon, there's all these things happening, and everyone knows everything, but no one really knows. But it's so big, right? And you can only do so much in a PhD.
Yeah.
So if you were to pick another factor, what would you pick, and why did you pick the ones you picked?
Okay. So the ones that I picked, I think, they were important because they all kind of were representing a very different challenge about how to communicating this. So for example, the subsea permafrost is a system that is not very directly influenced by human management, but it is very hard to study, and so it has very limited data. On the other side, the fires, they are very influenced by human management, but they're kind of modeling them is very difficult because so many interactions. And the water mega project, I felt that was just a general kind of problem that when we want to go with these hard solutions, with engineering solutions, so we just want to look at kind of different things about what was why we do make these kind of decisions. If I wanted to add one to what I had right now, I never thought about it. I don't know. I never want to add, maybe I wouldn't put this one. I never want to add anything. But
I don't know, PhD student have to do the same thing.
Yeah.
Everyone with a PhD is yeah, that's about right.
Let's add. But really, like pretty much anything that is regarding the future, I mean, all of our modeling has uncertainties. Isabella in our lab done another expert assessment for air pollution. And I think that the systems that are mostly are very complicated and they have several different interactions, especially with the human system. Those are the ones that maybe they need the most experts. So if I would do one more right now, maybe it will be on renewable energies and how we could like be sure that they're like effectively done and done in like in different countries they're done properly. Because one problem is that most of our knowledge is produced in Western countries, in developed countries, and so they're not very applicable to many other countries, and they are in conflict with their local conditions. So if I would want to do one of these expert assessment, I feel I would maybe do maybe renewable energies in more developing countries. So maybe that would be something I would be interested in.
Okay.
Yeah.
So to tie those two comments together, right? Just how you need to bring a diverse set of stakeholders together, and that there's this gap between what science can tell us and putting it into action so that things can happen in a timely way. And what would you do next? I think expert assessment is actually a really good way to get really quick information.
Yeah.
It may not be perfect, right? But that could kind of close this time gap that we have. So, but you sound exhausted.
No,
I would just say like this is really important, right? I think there's so many challenges that we have. They're time sensitive, and research does take a long time, right? So you have this expertise of like, doing this 3 times. And if there are any, you've identified a couple of other things that I think could really benefit from that, this kind of an assessment. So when you're well rested, I think you should keep tackling it.
Yeah.
Keep seeking funding. I was on a review panel, and I could see what you've done, the expertise that you've gathered, and it's clear like how important this is. Just encouragement. Great job.
Oh,
and get some rest and get back to it.
I have another question. You were trying to reach out to so many people, and I kind of remember some of the challenges that you had. Like, but what was the hardest part about reaching out to so many? Like, were most people responsive, or like, how was it? How was it like reaching out to the top of big issues?
So this was the most surprise for me, was that when I was doing this study, I remember with the permafrost one, I felt like when I was going to the conference, I personally thought that the younger researchers will be the ones who will be more willing to come because, well, there was a paper, so I thought like, that would be like a thing. And then it was to my surprise, there were not as much as like, they didn't understand like maybe what is the implications of this, and this kind of interdisciplinary research, I feel like kind of, it's out of people's comfort zone, and I feel like the most positive feedbacks I had from the more senior researchers, which I feel they have been in the field for so many years that they kind of really saw, oh, this is really a big problem, like we do all of this research and it's not available in time. So I had my best time with the more senior researchers, I feel. I also had a really good time with younger researchers, of course, but there were some people I feel like they didn't maybe get what we were wanting to do. For example, for the subsea permafrost, some people would say, oh, well, you're gonna do estimates, we went to the field, we went like gathered the data, and you wanna like give people, you wanna provide the numbers, that people would like use your study as like the numbers. Like that was a conversation I actually had with one of those younger researchers, like, I did all the field work and you're gonna, get the estimate. And I was like, well, I mean, these are like, they couldn't be more different. Like your study is like very specific, very deep, like it's such a different thing. And I felt like the main challenge was for me was like maybe this miscommunication about the purpose of the study. And I felt once that was resolved, people were much more open to participate and, share their data.
And do you
us to hold questions till the listeners can go?
No, you can, why don't we take 2 or 3 more minutes for open questions, and then we'll conclude. And yeah, if you've got a
I just
question.
have one,
put it on. Yeah.
question I think over. So this is, I'll ask Sarah about something I guess that's troubles me about like trying to influence policy and stuff. You talked about with the water projects, the mega projects, policymakers just doing their own estimates or finding their own experts that support them anyway. So I think that's one of these challenges we see is that like we can do as scientists, we can see why expert assessment should matter, right? But then a cynical perspective might say like, well, aren't most decision makers gonna just pick whatever information supports whatever conclusion they want anyway and just do what they want and justify it, right? The psychologists call this like motivated reasoning. So I'm curious, you've thought about this for 4 or 5 years now. Do expert assessments, do policymakers care about expert assessments? And I know they should care, and I think it's great, amazing what you've done. Like, love all of that. But like, what do you think in terms of like, do policymakers? I mean, some maybe, some not. But like, do policymakers care about this?
I feel it's very different based on the country and the government. So, for example, if I compare America with Iran, for example, in Iran, I would say no, they don't really care, and it's like a very specific situation. And for me, I feel in those countries, it's so important that we improve the general public knowledge, because for example, when I look from an ecologist's view in some of them are just like very obvious mistakes, and I feel like some of these should be just very common knowledge, and they're not common knowledge. So like we won't do some very obvious things, I don't know, to our body, because we have like maybe the general public are more interested about like their public health, like their personal health. But I feel like that kind of knowledge is lacking in environmental studies. So in those kind of countries, I wouldn't think they really care. Like that's my personal thing. But in more democratic countries, that policymakers do care about their popularity. I guess again, having that open discussions with public is really important, because I feel like having that making people happy and making decisions that will make them look good is really important. So I feel a really key thing here is the public, about like how public will respond to this, and I feel like policymakers, they mostly care about like how they will interact with the public, I guess. So I guess that's something that I feel that's a really important key that we consider.
So which of your 3 topics do you think is most politicized, and why?
I think so in general, I feel the permafrost is really important because of all of the energy resources in the Arctic countries, and I know a lot of the Arctic countries, they're not willing to share their data with each other, and so there are a lot of good data out there, but they're not sharing it because of these kind of political problems. And again, with the mega projects, I feel that's also something really politicized, because it seems like in many countries, for example in China, controlling water is just really a way of controlling power, and those two are being really associated together. So I feel those two are the most politicized, and I feel like in that respect, fires may be the easiest ones maybe to